You call that engineering? My 12-year-old nephew could design better with Lincoln Logs. That's how my Tuesday morning started, with some punk in a $3,000 suit telling me my 25 years of experience was worthless. Name's Patrick Sullivan, but everybody calls me Mac. I'm 48 years old, been building things since I could hold a hammer. Spent 4 years in the Army Corps of Engineers right after high school, then came home and worked my way through college nights and weekends while doing construction during the day. That was back when you could still do that, work full-time and pay for school without going into debt for life. I've been a structural engineer for 25 years now. Built bridges that'll outlast all of us, designed foundations for skyscrapers in earthquake zones, and never, not once, had a safety failure on my watch. My dad always told me, son, when you build something, you build it right the first time, because people's lives depend on it. That stuck with me. The guy calling my work garbage was Gavin Ashford, 32 years old, fresh MBA from Stanford, and the new CEO of what used to be Morrison & Associates. 3 weeks ago, his startup construction company bought us out. First thing he did was call a meeting to talk about optimizing legacy processes and streamlining outdated methodologies. In plain English, firing anyone with gray hair and replacing experience with computer algorithms. See, I've got this theory about young guys with business degrees. They think everything that came before them was done wrong, and they're going to fix it all with spreadsheets and innovative thinking. They've never had dirt under their fingernails or seen what happens when corners get cut on a job site. But they've got PowerPoints, so they must know better than guys like me who've been doing this since before they could drive. The project that was supposed to be my swan song was the Coastal Bay Bridge, an $80 million suspension bridge connecting the mainland to Harbor Point, where the state university sits. My son Ryan drives that route twice a day for his engineering classes. Kids following in the old man's footsteps, which makes me proud as hell. When I started designing this bridge 18 months ago, I kept thinking about him using it every day. This wasn't just another job. This was personal. The thing about bridge engineering, and this is something business school doesn't teach you, is that Mother Nature doesn't care about your profit margins. She's going to hit that structure with everything she's got. Wind, rain, earthquakes, temperature swings, and 40 tons of truck traffic every day for the next 100 years. You either build it right or people die. Period. But Gavin had other ideas about what right meant. The morning from hell started at 9 a.m. sharp. Gavin had called a design review meeting in the big conference room with floor-to-ceiling windows overlooking the construction site. He'd invited the board of directors, 6 guys in expensive suits who knew more about stock prices than steel grades, plus 3 junior engineers fresh out of college, kids who probably couldn't pour concrete without consulting Google first. I walked in carrying my tablet and a thick folder of structural analysis reports. 25 years of experience taught me to document everything. CYA, as we used to say in the Army, cover your assets. I had load calculations, wind stress analyses, seismic projections, and fatigue studies that would make your head spin. Every number double-checked, every variable accounted for. Gavin was already at the front of the room, wearing his usual uniform, charcoal gray suit that cost more than most people make in a month, Italian leather shoes, and that smug smile that said he was about to teach us all something. Behind him was a 75-inch screen showing my bridge blueprints blown up for everyone to see. Gentlemen, he started, clicking his laser pointer at the screen like he was conducting an orchestra, what you're looking at is everything that's wrong with American infrastructure today. This design represents old-school thinking that's bankrupting our industry. He zoomed in on the main support section. Look at these massive concrete pillars. Look at this steel specification, grade 50, which costs 40% more than standard grade. And look at these cable tensioning requirements. He turned to face the room with that practiced confidence they teach you in business school. This is what happens when engineers prioritize theoretical perfection over practical economics. I felt my jaw clench. Theoretical perfection? This kid had never calculated wind load in his life, and he was calling my safety margins theoretical. Sir, I said, standing up from my chair in the back row, those specifications aren't theoretical. They're based on 25 years of field data and the specific environmental conditions of this site. Gavin didn't even look at me, just kept staring at his screen like I was some heckler at a town hall meeting. And this is exactly what I'm talking about. Mac here represents the old guard, engineers who've been doing things the same way for decades, resistant to innovation, afraid of change. The junior engineers actually chuckled. These kids who'd never seen a construction site outside of a textbook were laughing at me like I was some dinosaur who didn't understand modern engineering. Now let me show you what optimization looks like, Gavin continued, clicking to the next slide. The next slide made my blood run cold. It was my bridge design, but butchered, like someone had taken a Rembrandt and painted over it with house paint. Here's the optimized version, Gavin announced proudly. By eliminating redundant structural elements and upgrading to modern efficiency standards, we've reduced project costs by $2.9 million while maintaining full safety compliance. I looked at the screen and felt sick. Where there used to be 6 main support pillars, now there were 4. The steel specification had been changed from grade 50 to grade 36. Cheaper stuff that's fine for warehouse construction, but not for a bridge that'll face 40-ton trucks and 60 miles per hour winter winds. And the cable tensioning specs had been cut to industry minimum standards instead of the site-specific calculations I'd spent months perfecting. I stood up again. Mr. Ashford, those aren't optimizations. You've reduced the safety margin below acceptable levels for this specific site. The wind load calculations alone— Sit down, Mac. His voice had an edge to it now. Nobody asked for your opinion. One of the board members, a guy named Richard with silver hair and a Rolex that cost more than my truck, leaned forward. What's the concern about wind? Before I could answer, Gavin jumped in. Mac here is obsessed with worst-case scenarios. He wants to build every structure like it's going to face a Category 5 hurricane. This is Northern California, gentlemen, not the Florida coast. When's the last time we had a major hurricane here? 1962? It's not about hurricanes, I said, trying to keep my voice level. It's about sustained wind patterns. The bay creates a tunnel effect that— Enough! Gavin's voice boomed through the room. This is exactly what I'm talking about. Mac represents everything wrong with the old guard. Fear-based engineering, paranoid overbuilding, resistance to progress. He clicked to another slide showing cost comparisons. Look at these numbers. Mac's original design, $80.2 million. Our optimized approach, $77.3 million. That's $2.9 million in savings that can go toward other infrastructure projects. That's efficiency, gentlemen. The junior engineers were nodding like bobbleheads. One of them, a kid named Timothy who probably graduated last spring, actually raised his hand. Mr. Ashford, what software did you use for the optimization analysis? Software. Jesus Christ. This kid thought engineering was about software. Excellent question, Timothy, Gavin beamed. We used CostMax Pro integrated with Structure Optimizer 3.0. It analyzes thousands of variables simultaneously to find the optimal balance between safety and economy. I couldn't help myself. Did your software account for the specific wind patterns at this site? Did it factor in the harmonic resonance frequency of the reduced support structure? Gavin looked at me like I was speaking a foreign language. Harmonic what? Mac, this isn't rocket science. It's a bridge. Steel, concrete, cars drive across it. We don't need to reinvent physics here. That's when I knew this kid was dangerous. He didn't understand that bridges are living things. They flex, they vibrate, they respond to forces in ways that can't be captured in a computer program. You learn that by standing on job sites during windstorms, by watching how structures move under load, by seeing what happens when some hotshot cuts corners. For the next 2 hours, Gavin systematically shredded every decision I'd made. When I explained why the concrete mix needed specific additives for salt air resistance, he called it gold plating. When I detailed the cable anchor requirements, he said I was overthinking simple connections. When I brought up seismic considerations, this is California for crying out loud, he said I was paralyzed by fear of unlikely scenarios. Every time I tried to explain the engineering behind my choices, he cut me off. Nobody wants a physics lecture, Mac. We want solutions. Or, this is business, not engineering school. Or my personal favorite. Maybe it's time for the old generation to trust the new generation's fresh perspective. The worst part wasn't the insults. It was watching those board members nod along and seeing those young engineers take notes like they were learning gospel truth. I could see them thinking, this old guy just doesn't get it. Progress means doing things smarter, not harder. Around 11:30, Gavin really went for the throat. You know what Mac's problem is? He announced to the room like I wasn't even there. He's been doing things the same way for 25 years. He's comfortable with the old methods. Change is scary when you're close to retirement. Close to retirement. I was 48 years old with a kid in college and a mortgage. But to this punk, anyone over 40 was ready for the glue factory. Look, he continued, I get it. Mac built his reputation on being the cautious guy, the safe choice. But cautious doesn't win contracts in today's market. Clients want efficiency. They want innovation. They want results, not excuses. He pulled up a photo of the partially completed bridge foundation. See that concrete work? That's Mac's design. Solid, sure, but way overbuilt. We could have achieved the same result with 30% less concrete and half the rebar. But Mac doesn't trust modern materials science. He builds like it's still 1995. One of the board members asked, "So what happens to the existing foundation?" "We adapt," Gavin said smoothly. "The good news is concrete is forgiving. We can build the optimized superstructure on Mac's overbuilt foundation. Actually gives us even more safety margin than we need." Safety margin. This kid was talking about safety margins while gutting every real safety feature in the design. It was like watching someone remove the brakes from a car while bragging about how much weight they'd saved. By noon, I was grinding my teeth so hard, my jaw hurt. Gavin had convinced the room that my bridge was a dinosaur designed by a dinosaur, and that his optimization was the future of American infrastructure. The board voted unanimously to approve his changes. "Don't look so glum, Mac," Gavin said as people filed out for lunch. "I know change is hard for your generation, but trust me on this one. In 6 months, when this bridge opens on time and under budget, you'll see I was right." That afternoon, sitting in my truck in the parking lot, I did something I hadn't done since my dad died. I felt like crying. 25 years of building things right, of following the code, of putting safety first, and this is what it got me. Public humiliation from a kid who thought engineering was a software problem. But then I thought about Ryan driving across that bridge every day, and I got mad instead. That night, I couldn't sleep. Every time I closed my eyes, I saw Ryan's face when I'd have to tell him his old man got shown up by some kid with a business degree. But worse than that, way worse, I kept thinking about what those optimizations really meant. Around 2 a.m., I gave up on sleep and went to my home office. I fired up my laptop and pulled out my original calculations. Not because I had to anymore, Gavin had made it clear my input wasn't wanted. But because I'm an engineer, and engineers don't just take someone's word for it, we check the math. The first thing I did was run the wind load calculations on Gavin's optimized design. With only 4 support pillars instead of 6, the load distribution completely changed. I punched in the numbers for sustained 35 miles per hour winds, typical for winter storms in the Bay Area, and stared at the results. My hands started shaking. With the reduced support structure and cheaper steel grades, the bridge would start oscillating at sustained winds of 35 miles per hour or higher. Not violent shaking at first, just a gentle sway. But here's what that Stanford MBA didn't understand about physics. Resonance builds on itself. Like a kid pumping their legs on a swing, each cycle adds more energy to the system. I'd seen it before. Hell, every structural engineer has seen the footage of the Tacoma Narrows Bridge collapse in 1940. Beautiful suspension bridge, built to code, destroyed by resonance when 40 miles per hour winds hit it at just the right frequency. 2,800 feet of steel and concrete twisted apart like a ribbon in the wind. But Gavin's bridge wouldn't collapse right away. The oscillation would create metal fatigue in the cables and stress fractures in the support connections. Give it 5 to 7 years, and those optimized components would fail catastrophically. Probably during a winter storm when the bridge was loaded with commuter traffic. Ryan made that drive twice a day. I spent the next 3 hours running scenarios, hoping I was wrong. I checked my calculations 4 times. I even used that CostMax Pro software Gavin had mentioned, downloaded a trial version, and fed it the real site data, not just the generic inputs his people had used. The software confirmed what I already knew. The bridge was a disaster waiting to happen. By 6 a.m., I was drinking my 3rd cup of coffee and staring at the most disturbing part of Gavin's design. He'd added something that wasn't in my original plans, an innovation observation deck for VIP visitors. A glass-enclosed platform positioned about 50 feet from the main construction area, elevated to give dignitaries and investors a perfect view of the bridge work. I pulled up the positioning coordinates and felt my stomach drop. The observation deck was located at the exact mathematical center of the resonance zone. When those 35 miles per hour winds hit the completed bridge, that platform would experience the maximum oscillation effect. Anyone sitting there during a windstorm would feel like they were on a boat in rough seas. But here's the beautiful part. And I mean beautiful in the way only an engineer can appreciate irony. Gavin had designed his own trap without knowing it. I sat back in my chair and actually smiled for the first time in 2 days. This kid thought he was so smart, cutting corners and saving money. He'd built himself a front row seat to experience exactly what happens when you ignore physics. Over the next week, I watched the construction progress from my office window. The concrete work was moving along. My foundation design, which Gavin had called overbuilt, was solid as a rock. The steelwork was starting to go up, and I could see where they'd changed the specifications. Thinner support beams, fewer connection points, cheaper materials throughout. It looked fine to the casual observer. Hell, it probably looked pretty good to Gavin's software, but I could see the weakness points like cracks in a windshield. Thursday morning, Gavin called another meeting. This time, it was for the VIP preview tour with potential investors for his next project. He wanted to show off the bridge construction as proof that his cost-cutting approach worked. 8 investors from some big development firm in San Francisco, plus a couple reporters from the local business journal. Perfect. I spent Thursday afternoon borrowing some equipment from the materials testing lab. Nothing fancy. Just a frequency generator and a small industrial fan, the kind we use to test how structures respond to wind loads. I also grabbed my tablet with the wind monitoring app and my trusty laser measure. The forecast for Friday showed sustained winds at 38 miles per hour, gusting to 42. Mother Nature was going to provide the perfect conditions for a little physics demonstration. That night, I called Ryan. Just to hear his voice, you know. He was excited about some project in his engineering mechanics class, talking about load calculations and stress analysis. Smart kid. He actually understood what his old man did for a living, unlike certain CEOs I could mention. "Dad, you sound tired," he said. "Everything okay at work?" "Yeah, son. Just dealing with some new management." "You know how it is. That sucks. Hey, I drove past your bridge site yesterday. Looks like it's really coming along. Can't wait to use it instead of driving all the way around the bay." And that's when I knew I was doing the right thing. This wasn't about ego or revenge or showing up some arrogant kid. This was about protecting my boy and every other kid who'd use that bridge. Friday morning arrived gray and windy. Perfect weather for an engineering lesson. I got to the site early and set up my equipment on the main construction platform, about 50 feet from Gavin's observation deck. The frequency generator was small enough to fit in a toolbox, and the fan looked like standard construction equipment. Just another old engineer checking wind loads. At 10 a.m. sharp, Gavin arrived with his entourage, 8 guys in expensive suits looking like they'd rather be anywhere else. They all piled into the observation deck, a fancy glass box with leather chairs and a killer view of the bay. Gavin sat right in the center, in what he dubbed the founder's chair. He was positioned exactly where my calculations said the resonance effect would be strongest. "Gentlemen," Gavin announced, settling into his chair like a king on his throne, "welcome to the future of American infrastructure. What you're seeing here is proof that smart engineering can deliver better results for less money." I checked the wind speed on my tablet, 38 miles per hour sustained, gusting to 41. Perfect conditions. Time to show these folks what smart engineering really looked like. One of the investors, a tall guy with silver hair, raised his hand. "Mr. Ashford, what about the wind load concerns? I understand the original engineer had some reservations about the structural modifications." Gavin waved dismissively in my direction. "That's Max Sullivan over there. 25 years of building bridges like they're going to survive nuclear war. Old school mentality. If it's not massively over-engineered, he considers it unsafe." He leaned back in his founder's chair, spreading his arms along the leather armrests like he owned the world. "The fact is, gentlemen, modern engineering allows us to optimize for both safety and cost. Mac represents the old guard, guys who've been doing things the same way since the Carter administration." That got a few chuckles from the suits. Perfect. I walked closer to the platform railing carrying my tablet. "Actually, Mr. Ashford, mind if I show these gentlemen something interesting about your optimization approach?" Gavin looked annoyed but maintained his smile for the investors. "Make it quick, Mac. These are busy people." "Well, see, engineering isn't just about software optimization," I said, loud enough for everyone to hear. "It's about understanding how structures respond to real-world conditions, like wind." I gestured to the wind meter readings on my tablet. "Right now we've got sustained winds at 38 miles per hour, gusting to 42. Perfect conditions to demonstrate what happens when you modify load-bearing specifications without accounting for harmonic resonance. One of the investors leaned forward. Harmonic what? Resonance frequency, I explained, pulling the frequency generator from my toolbox. Every structure has a natural vibration frequency. When external forces match that frequency, the vibration amplifies, like when an opera singer hits the right note and shatters a wine glass. Gavin rolled his eyes. Here we go with the physics lecture. Mac, nobody needs a science experiment. This bridge is engineered to code. Your code, maybe, I said, but not Mother Nature's code. I positioned the frequency generator and the industrial fan to simulate the wind load patterns that would hit the completed bridge. The equipment was small enough that most people probably thought it was just standard testing gear. Gentlemen, I recommend you step back about 10 feet from the observation deck, I announced. This demonstration will show you the real-world effects of the structural modifications. The investors looked nervous but moved back. Gavin stayed put, arms crossed, smirking like he was about to watch me make a fool of myself. Go ahead, Mac, he said. Show us your little magic trick. Prove whatever point you're trying to make. I activated the frequency generator and positioned the fan to match the wind angle calculations. The modified bridge design, I explained as the equipment hummed to life, has a resonance frequency that matches typical Bay Area wind patterns. When sustained winds hit 35 miles per hour or higher, the structure oscillates. The effect started subtly. The observation deck began to sway gently like a boat on calm water. Gavin's confident expression shifted to confusion as his chair started rocking. The observation deck, I continued, increasing the frequency to match the wind load, is positioned at the mathematical center of the oscillation pattern. What you're experiencing now is about 20% of what the completed bridge will experience during a typical winter storm. The swaying increased. Gavin gripped the armrests as his chair rocked back and forth. The glass walls of the deck amplified the motion, making it feel like being inside a snow globe that someone was shaking. What the hell is happening? Gavin demanded, his voice tight with alarm. Physics, I said calmly. This is what happens when you cut support pillars and downgrade steel specifications. The structure becomes vulnerable to resonance oscillation. One of the investors stepped forward, looking pale. Are you saying this bridge will collapse? Not immediately, I replied, adjusting the frequency to match peak resonance. The oscillation creates metal fatigue in the cable connections and stress fractures in the support joints. Give it 5 to 7 years of regular wind loading and those optimized components will fail catastrophically. Gavin was now visibly nauseous, his face turning green as the platform continued its rhythmic motion. Turn this off, he yelled. This is some kind of trick. No trick, I said, just engineering. The frequency generator is simulating what 40 miles per hour winds will do naturally to your modified design. Except in real conditions, this motion would be about 5 times stronger. Another investor was already pulling out his phone. Jesus Christ, we need to shut this project down immediately. You're telling us this thing is a death trap? Gavin stumbled out of his chair, holding his head. Mac, stop this. I'm going to be sick. I turned off the equipment. The swaying ceased immediately, but Gavin continued staggering for several seconds before collapsing onto the platform floor. That, gentlemen, I said, is what every passenger on this bridge would experience during a winter storm. Except they'd be traveling at 60 miles per hour in 2-ton vehicles when the resonance hits. The aftermath was swift and brutal. The investors pulled their funding that afternoon, citing catastrophic safety concerns and gross engineering negligence. The State Highway Commission ordered an immediate suspension of construction pending a complete safety review. When the independent engineering team arrived 2 days later, they confirmed every single one of my calculations. The modified design was structurally unsound and would have resulted in bridge failure within a decade. Gavin was fired before the week was out. The best part? They asked me to redesign the entire project from scratch. This time with full authority to enforce every safety specification I deemed necessary. No more optimizations, no more software overriding experience, just solid engineering built to last. 3 months later, Ryan called me from his structural dynamics class. Dad, my professor just used your bridge redesign as an example of proper resonance analysis. He said it's textbook perfect for wind load distribution. That's when I knew I'd done more than just save a construction project. I'd protected my son's future, preserved the integrity of my profession, and proved that experience still trumps arrogance. The new Coastal Bay Bridge opened 8 months later. built to my original specifications with a few modern improvements. It's designed to handle anything Mother Nature can throw at it for the next 100 years. And yes, there's still an observation deck for VIP visitors. But this time, it's positioned where physics says it should be, not where some MBA thinks it looks impressive. As for Gavin, last I heard he was selling insurance in Phoenix. Turns out there's not much demand for structural engineers who don't understand structures. And me? I'm 48 years old, got 17 years left until retirement, and my son respects his old man's work. Some days, that's all the victory an engineer needs. You see, there's one thing they don't teach you in business school. Physics doesn't care about your PowerPoint presentation or your profit margins. When the wind blows and the steel bends, the only thing that matters is whether you built it right the first time. And that knowledge only comes from guys who've been there when things go wrong.